In the second section of the Monte Carlo Simulation Introduction course, we compare the PERT and triangular distributions. In lessons 12, 13, and 14, we analyzed their differences but left a definitive conclusion pending. We will now complete that comparison. To do this, we go to the parameters sheet, cell B8, and first select the PERT distribution. This distribution, like the triangular one, requires three parameters: a minimum, a mode, a most likely value, and a maximum. The difference lies in the shape of the curve. PERT is smoother, while triangular has straight lines. When selecting PERT, it is applied to task durations, fixed and variable costs, and risk impacts in both duration and cost. Now we run a simulation with 20,000 iterations and store the results in the outputs sheet, specifically in column I, using the 70th percentile as a reference, since this is the recommended level for IT projects based on common practices discussed in the previous lesson. Then, in cell B8, we change the distribution to triangular and run the simulation again with 20,000 iterations. We save these new results in column J to compare them with the previous one. Now we compare. Remember that based on the randomness principle of Monte Carlo simulation, the results reported here will likely differ slightly from those simulated at different times or by different users, especially if the number of iterations is low. Now we have column I, results with PERT, column J, results with triangular, column K, a percentage comparison between both. For example, with PERT, the project finishes on August 8th, 2026. With triangular, it finishes on August 13th, 2026. That's a 5-day difference, which might seem minor but affects total duration. PERT, 161 days. Triangular, 165 days. The same applies to costs. PERT, 30,923. Triangular, 32,139. This represents an increase of nearly 4% in costs and 2.5% in duration. Now, which distribution to use? It will be up to the analyst's judgment to decide whether these differences are significant enough to prefer one distribution over the other. In lessons 12 to 14, we discussed the pros and cons of both. This analysis was conducted using 20,000 iterations in both cases. But what happens if we only use 200 iterations? Simulations with a low number of iterations, 200, results in fragmented, less precise graphs. This often occurs in student or free versions of the software that have limitations. When we increase the number to 20,000 iterations, the results become more stable. To test this, we ran 10 simulations with only 200 iterations and compared. The mean result was 31,061. The 70th percentile was 32,186. Based on this data, we calculated the coefficient of variation. For the mean, it was only 0.46%. For the 70th percentile, 0.72%, which in at least on one case represented an overestimation of contingency by about 2% when using only 200 iterations. This shows that while the mean stabilizes quickly, percentiles require more iterations for better accuracy. Our general recommendation: attach charts show histograms based on 200 and 20,000 iterations respectively. Our recommendation is, for educational purposes, a rough approximation using just 200 iterations is acceptable. For professional use, we recommend using at least 5,000 to 10,000 iterations as a practical rule of thumb to ensure reliable convergence in project or business simulation models.